Bismillahirrahmanirrahim. In this chapter, discussion on virtual memory continues and we'll discuss some more topics related to virtual memory. Since virtual memory is quite an intensive topic, so I have divided it in two chapters. In previous chapter, we have seen different techniques of virtual memory, and in this chapter again we would discuss some more techniques related to virtual memory. What all we are going to discuss? Let's see the outline for this chapter. This is all what we are going to discuss in this chapter. We will first recap the topics we have already discussed in order to develop your background. Then the concepts in virtual memory will be discussed that include demand paging, page fault, different page replacement techniques or algorithms, the address translation using direct and associative mapping, and at the end, pre-paging concept will be discussed. Before moving ahead to discuss different concepts related to virtual memory, we first need to develop your background. What is virtual memory? As we said in previous chapter, that virtual memory is physically part of secondary storage, but it acts as second RAM in order to provide a logical address space for the processes. Processes need to be loaded to actual RAM for execution, and execution does not take place from virtual memory. Virtual memory only provides a boost to actual RAM in order to enhance its storage capacity. RAM is known as physical memory, while virtual memory is known as logical memory. Since virtual memory is part of secondary storage, hence it has larger storage space as compared to physical memory, which is RAM. We already have seen the memory hierarchy in previous chapters. Virtual memory is also shared among different processes, and more than one process reside in virtual memory. Virtual memory can be implemented using two techniques, which are demand paging and demand segmentation. We already have discussed paging and segmentation in previous chapter. So, demand paging and demand segmentation techniques both are applied on pages and segments respectively. They both work similarly, so I will be discussing one of them and the other works the same. This figure shows the difference in the capacity of both physical and logical memory. Since virtual memory is part of secondary storage, so its storage capacity is higher than the physical memory. Pages or segments are mapped from virtual to physical address, and from physical address they may again swap out to virtual storage, which resides on secondary memory. So, virtual memory, this is physically part of your secondary storage, and pages are swapped out from physical memory to secondary memory. I hope you have developed your background. Next, now we will be moving towards demand paging. And let's see what is demand paging. What is demand paging? As the name indicates, demanding a page, that means a page is loaded in RAM only when it is needed. There are different benefits of demand paging, such as less I/O would be required by pages, as by large those pages will be loaded that are CPU bound than I/O bound, as demand goes mainly for CPU bound processes. Second benefit is less memory is required if only needed processes will be loaded in main memory. Instead of wasting memory with blocked or unused pages, it is better to use memory efficiently by loading only needed pages or segments. Another benefit is faster response, and it is due to the fact that CPU will be more busy in executing instructions within the pages or segments, and quick response will be generated from CPU. Next benefit for demand paging is that more users will be supported, as pages of more than one processes of different uses will be allowed to be stored in RAM. How demand paging is implemented? Whenever a page is needed, it is referred or referenced. Now there are two situations. If the reference is invalid, as you can see, first point, if the reference is invalid, that means the page is not present in the main memory. So that reference is aborted. While the second situation may be, as you can see, if the reference is valid, that means the page is not present in main memory and is located in logical memory. So then that page is loaded in RAM. Here, the swapping mechanism is shown. The pages which are blocked are swapped out of main memory to virtual memory, while the required or demanded pages are swapped in back to main memory. So swapping mechanism is shown in this diagram. We already had discussed valid, invalid bits in previous chapter. Every entry of page table has valid, invalid bit associated with it. Valid is represented as 1. That means specific page is present in main memory, while invalid bit is represented as 0. That means specific page is not present in main memory. Initially, all entries for a process in page table are set to 0. When address translation happens, and if a reference page has 0 bit with it, so page fault occurs. Now, what is a page fault? Next topic of discussion is page fault. So let's see what is a page fault. If a reference to a page is traced to 0 in page table, so page fault occurs, which means the required page is not present in memory. Page fault acts as a trap for operating system because operating system leaves everything and tries to search out the required page in secondary memory. Searching secondary storage takes a lot of time as it has higher storage capacity. Now for 0 bit, operating system has to be very careful to identify if the frame is invalid or the page is just not in main memory. After confirming it, if the reference is invalid, the instruction referring that page is aborted. But if it is just not present in main memory, so operating system would load that page in main memory. For loading a page in memory, operating system needs to first create space for it in RAM. Operating system first has to find a free frame. Then swap in the required page in that frame. Once the page is moved in the particular frame, so the page table entry for respective page will be updated. Initially, its validation bit was 0 and now it has to be set to 1. Once page table entries are updated, then the instruction referring to this page is restarted. This is how page fault is handled. All the steps discussed in previous slide are represented diagrammatically here. Step 1 is a page is referenced by a running page in RAM. So operating system indexes that page in page table, and if its validation bit is found 0 or I, that means it is invalid. The invalid bit traps operating system and results in page fault as shown in step 2. Operating system searches the page in virtual memory as well as the secondary storage as shown in step 3. If the page is found in secondary storage, operating system has to then find a free frame for it in physical memory as shown. So, in step 4, operating system loads that page into the free frame in physical memory. Operating system then resets the page table entry and sets its protection bit from 0 to 1 as shown in step 5. Then the instruction from running page that referred this page gets restarted as shown in step 6. I hope the whole page fault mechanism must be understood to you all. Now, what happens if there is no free frame in physical memory? Operating system has to then swap out the blocked page to secondary storage or virtual memory, and the required page is replaced with the swapped out page. Best suitable page replacement algorithm is applied, the one which will result in less number of page faults, as page fault acts as a trap for operating system. In any page replacement algorithm, the demand for a single page may happen again and again. So, it has to be ensured that such a page may be brought in memory many times. So, consideration should be given to this point that only one page must be brought in memory one time. Its multiple instances should not be copied anywhere else in main memory. Next topic of discussion is page replacement. So we will see what is a page replacement and how different page replacement algorithm works. Page replacement is implemented very smartly by slight modifying the page fault service. Another bit is added with every entry of page table, and that bit is known as modify bit, also called as dirty bit, so that memory is not over allocated with same pages. A page that has been modified by the user, so its modify bit will be set to 1. Modified means updated or user made any change to the specific page. If a page has been modified by user, so only then it would be reloaded in memory. Otherwise, its previous version is enough to keep on working. A page is replaced to and from virtual memory as it acts as second RAM, having higher storage capacity than actual RAM. And you all know virtual memory is also known as logical memory. How page replacement works. First, when a page fault occurs, operating system finds the required page on secondary storage. Then operating system finds a free frame in RAM for the page to be loaded there. If it finds a free frame, the page gets loaded there. But if all the frames are occupied, then operating system activates the suitable page replacement algorithm to swap out a blocked page from RAM to disk, and the required page from disk is swapped into that frame. The page table entries of both the pages are updated. The one swapped out and the one swapped in. Swapped out page now has its valid invalid bit reset to 0, which was 1 before swapping, while the swapped in page had its valid invalid bit set to 1, which was 0 earlier. After doing that, the instruction that has referred this page gets restarted. This is how the page replacement procedure works. If free frame is not available, only then page replacement algorithm is activated. Operating system selects a victim page present in RAM that has to be swapped out in order to create a free frame for the coming page. The victim page is swapped out to secondary storage as shown in step 1, and its page table entry gets updated by resetting its valid invalid bit to 0 as shown in step 2. The required page then is brought into RAM from secondary storage as shown in step 3, and its respective entry in page table is updated from 0 to 1 as shown in step 4. So an old page has been now replaced with the new one. That is all for now. We will continue our discussion on page replacement strategies and discuss different algorithms for page replacement in the next lecture. I thank you all.